Now, I want to show you how those combinations of neutrons and protons, electrons, produce all of the atoms in the visible universe. I have shown here, this is all of the atoms in the visible universe. There's only about 3,000 different types of atoms. The neutron is here. This is energy or mass. And the neutron has slightly more mass than does the hydrogen atom or the electron-proton pair. So this thing spontaneously decays to that one. As long as it's got a negative slope, that can happen. The simplest atom is if the simplest atom consisting of electrons, neutrons, and protons is when a neutron and a proton come together. And that makes the deuterium atom. And that atom is this point right here. So this is like a proton and a neutron together make the deuterium atom. That's like a north and a south end of a magnet that are together. If you have, instead of just one neutron and one proton, if you have two protons and two neutrons, that's like this. That is much more stable structure. Because that is bound more tightly, the mass decreases. This is deuterium, this is helium. So this is like the helium nucleus. This structure is very stable. In fact, it's more than halfway down to the very bottom to the most stable configuration you can get. By the time you put two pairs of the electrons, neutrons and protons, you're more than half the way down. So the helium nucleus is surprisingly stable. If the helium nucleus is combined with if three of these helium nuclei are combined together, this is helium, that's helium, that's helium. That makes carbon. So this is deuterium. This point, can you see that one, is helium. This next point is carbon. If you added another helium nucleus to carbon, this would represent oxygen. So deuterium, carbon, oxygen. The most stable possible configuration of atoms is given by that of iron. By the time you get, now as you're putting these things together, remember the neutrons are repelling neutrons and protons are repelling protons, but the neutron-neutron interaction is not quite as repulsive as the proton-proton. The net result is as you keep stacking these things together, by the time you get to the very bottom, you've got iron 56. That's the most stable configuration. Iron 56 consists of 26 pairs of neutrons, protons, plus it has 4 extra neutrons. So to account for the fact that proton-proton interaction repulsion is a little stronger than neutron-neutron interaction, as you build heavier and heavier atoms, you shift and have a little excess of neutrons. To make it easier for you to see the 4 nuclei that we've talked about so far, I've drawn circles around them. This is deuterium. That's 1 neutron, 1 proton, and 1 electron. Deeper yet is the helium nucleus. That's two neutron-proton pairs. The next one that's circled is the carbon atom. That is 6 neutron-proton pairs. And next is the oxygen atom. That is 8 neutron-proton pairs. And the most stable of all nuclei is shown with this red dot. That's iron 56. The heaviest of all stable elements is element number 83. That is bismuth. Bismuth contains 83 neutron-proton pairs plus an additional 43 extra neutrons to compensate for the fact that proton-proton interactions are stronger than neutron-neutron interactions and all of those that we've added to make that bismuth nucleus. Beyond bismuth, the next element in the actinide elements, the one that was used for the first reactor and for the first bomb, was uranium-235. Uranium-235 contains 92 pairs of neutrons and protons, plus an additional 51 neutrons. When one more neutron is added, that nucleus breaks apart. That's what powered the first reactors. That's what powered the first bomb, the first atomic bomb.